All right, this is going to be a quick video about the Doppler effect. The Doppler effect is a change in frequency that's observed when either you're moving towards the source or moving away from the source of the sound, or the source could be moving towards or away from you. The most common example here, the classic example, is of a race car moving past you when the initial sound of the engine of the race car sounds quite high in frequency, and then as the race car passes, it appears to shift lower. Um, the idea here is if we imagine, I always like to think of a duck for some reason with this. So this is going to be our duck, okay? And our duck is swimming in a lake, and let's say there's a tap over here in the lake that is producing drops of water. Okay, so that's a tap that somehow randomly exists. Maybe this is a bathtub or something like that where you're playing with a little toy duck. And so the drops of water are creating waves. So the waves are going like this out to the duck. And if the toy duck is stationary, then the frequency with which these waves are generated will match the frequency that the duck is bobbing up and down. But if we imagine taking the duck and pushing it, or it's swimming towards the source of the tap, then as it swims, it's going to run into these wave fronts a little sooner than it would have had it stayed still. See, it's moving towards them at the same time as they're moving towards it. What that means is, as the duck moves this way, it will reach the wave fronts a little faster. This means it will experience a few more waves in a set period of time. If it experiences a few more waves in a set period of time, that effectively means the frequency that it observes will be greater than the frequency generated by the tap. This is all if the duck moves towards. We can make the same argument if the duck is moving away. Let's say that he goes this way instead. If he does, then it'll take those wave fronts a tiny bit longer to reach them than they otherwise would have. This means that the duck will experience a wave front a little less frequently than we would have expected based on how the wave fronts are being generated. So if the duck is moving away, the frequency appears to be less than that of the frequency generated at the tap. So that's if we imagine the person observing the sound is moving relative to the generated sound, either moving towards, increasing the frequency, or moving away, decreasing the frequency. So towards is an increase and away is a decrease. But we can make a similar argument if we imagine the motion of the source itself. Imagine a source at t equals 0 generates a wave, and that wave has time to spread out, and as a result, it forms a fairly large circle around where it was generated in the first place. And then at t equals 1, it generates a second wavefront. This second wavefront will not have as much time as t equals 0 to spread out, so maybe it's going to be about this big. And then at t equals 2, we have a third wave generated, and that third wave has very little time to spread out, so he's only little. Now what we can see here is the source of our wave is moving left to right. And what that means then is that the wave fronts going from left to right have become very compressed with result to each other. If we imagine an observer standing here where the source is coming towards, those wave fronts are going to come together faster than they would have otherwise. And so here we expect that the frequency will appear higher. Alternatively, if we imagine a person who's observing this sound as the object moves away from him, these wave fronts are artificially spread out. And what that means is the frequency will appear lower. So this is if it's moving towards, and this is if it's moving away. Either way, whether you're a duck swimming towards something generating a wave, or whether you're a person listening to a race car traveling past you, if the object is moving towards you, what that means, or if you're moving towards the object, those wave fronts will meet you a little bit faster than they would have otherwise. If it's moving away from you, they'll take a little bit longer to reach you than they otherwise would have. Towards means that the frequency appears higher, a little bit less time than expected. Away means the frequency will appear lower. They're taking longer, so they are less frequent. Mathematically, the Doppler effect can be summarized by this equation. FO here is the original frequency. F then is the observed frequency. And we can see that it's a ratio of the speed of sound and the speed of the object. So the speed of sound divided by the speed of sound plus the speed of the object or minus the speed of the object. Now that VO could represent the speed of the object or the speed of the source. It doesn't make any difference. Sometimes it's written as the relative motion between the source and the object. The plus here will make the denominator bigger and make the observed frequency smaller. And so the plus works if the object is moving away from each other, the object and source are moving away from each other. And the minus here makes the denominator smaller, which will make the overall observed force bigger, which means we want that equation if the objects are moving towards each other. So the plus is for away, and the minus is for towards. That's the Doppler effect.